Welcome. Today I'm going to be talking about jacking forces and a little bit about roll centers and how the two are related. There's lots of videos on roll centers, so I won't be going into them too much. And to start off, first I want everyone to understand the coordinate system I use. So looking at a model of my old Audi. We have the car forward, and if you look at the coordinate system is X, to the left is Y, and then vertical is Z. I'm going to be saying FY or FZ or Z-axis, Y-axis. So just know those are the directions that I'm talking about when I say that. To quickly go over what roll centers are, we'll look at the sketch here. So we have the wheel center line, left and right, and then upper A-arms and lower A-arms, and lines projected from the A-arms. And where they meet is the instant center. So the instant center is going to have a vertical and a lateral dimension to it. Then if we take lines from the bottom of the wheel contact center and project or draw a line from the wheel center to the instant center, we'll get these two lines, and where they cross is the roll center. So as the suspension moves throughout its travel, the angles of the A-arms will change, and the instant center will move as well. And then you'll continue drawing the lines from the wheel center to the instant center, the dynamic point of them. So your roll center may or may not move as suspension travels. So what is jacking force? We'll go back to our sketch. We have our wheel here, we'll call our outside wheel or outside tire. And there will be a lateral component of force that the tire is creating. That lateral component has to be reacted, and it's reacted by the A-arms. So there's a lateral component of the A-arms that is reacting the lateral component of the tire force. Since the A-arms are at an angle, there's going to be not only a lateral component, but also a vertical component of the A-arm force. So the vertical component is the jacking force. Since both A-arms, as I have them drawn at least, are at an angle, both are going to create a vertical component or jacking force. If, let's say, the lower A-arm was straight horizontal, then there will be no vertical component from that A-arm. And the vertical component, since it is going into the chassis is partly suspended vertically by the A-arms, and the other component would be the other vertical component. The rest of it is supported by the springs and dampers. For my calculations, I like to simplify it. I just take the instant center location, and I know the wheel center location, and I draw a line between the two. We'll call that the end line. So you take the vertical or lateral component of the tire force, and you'll have this known angle of the end line, so you can calculate the vertical component of the force. And I use that as a jacking force. So why would you use jacking force? We're using the roll center to calculate weight transfer. You'll get weight transfer of how much your left and right, front and rear load on your tires is changing, which is good. You can use that to tune your car. Just know that it is a simplification, and it won't necessarily be exacts, but you'll get the change, if that makes sense. So it may say you get 100 pounds more weight transfer from changing your roll center from whatever 1 inch to 2 inch. It may not actually be 100 pounds in real life, but there will be an increase of some kind, and you can use that to tune, which is good. It's real simple, it's quick. Jacking force, you get the same thing, but you also get the vertical component, the Z, so you can find the ride height change of your car. And this is important if you have aerodynamics, front rear wings, spoiler, under tray, whatever you may have. They're all going to change the coefficient of drag and coefficient of downforce depending on the ride height. So if you have an aeromap that maps out front and rear ride height versus drag and downforce, then jacking force is definitely needed, so you can use that aeromap in your simulations. There's also a component for jacking force in transients. Using jacking force, you can see how you can change your turn in and balance and turn out of your car, and I'll show you that later. But first we're going to get into static calculations. So here's a spreadsheet I created to calculate the jacking force. Start off, I just have my inputs. There's no weight distribution because I'm just using one axle. So we have the total mass, CG, lateral G of what do you want to calculate for lateral G force, the half track of left and right, spring stiffness, ARB, motion ratio for the springs and ARB, static ride height, the tire stiffness, which for this purpose I'm just leaving out, but you can always add that in later. And then the front view instant center, both the Y and the Z location of them for the left and right. And then using all those inputs, I just have calculations of anti-roll stiffness, wheel rate, spring and anti-roll bar, and just the wheel rate of the springs. And then just a ride frequency. It's just let you know where you're at. It's not using any calculations. And the peak lateral force of the tires, which is using the lateral G and then the dynamic corner weight, just to give a number. There's no sensitivity for the tires for lateral force, although I do have calculations for it. So basically, as you increase your normal load, your coefficient of friction is going down. But for what I'm going to show, I've ignored this and you just use simple, it's 1. And then after you create your spreadsheet, you can add in things such as tire sensitivity. But for now, it's just kind of the basics. So we start with the jacking force calculation, taking the lateral tire force, and also have total lateral weight transfer. So it's just weight transfer calculation, overall weight transfer, ignoring jacking force and elastic weight transfers. Is total weight transfer of the car, which is going to always be dependent on track width, CG height, lateral force, and using the total mass of your car, you'll get your total weight transfer. And then I use the contact patch instant center angle, or the N line. I find the angle for each one. And then using the N line and the lateral tire force, I'm calculating the jacking force. So it's just the tangent of that N line times the, or tangent of the N line angle times the lateral tire force, and you get the vertical component. And that's your jacking force. So how do we use all this? So I just found my static corner weights, and then static elastic weights, just the same as the static corner weight. Static wheel displacement. So it's just how much the springs are compressing under the static corner weight. Then, using the calculations from up here, I find the dynamic corner weight, which is just taking static corner weight and subtracting or adding the total weight transfer. So subtract it from the inside and add the weight transfer to the outside. And then, using the dynamic corner weight, subtract the jacking force, and you'll get the elastic corner weight. So this is the weight that is going through your springs. And then using the dynamic corner weight, I just found the new wheel displacement, using the elastic corner weight, because that's the weight going through the springs. That's the weight that's actually going to change your ride height, I find the wheel displacement. And it looks like I actually did use tire displacement using the vertical tire stiffness. But if you want to simplify things, you can just leave that out. And using the wheel displacements, I find my roll angle, and then I find my ride heights, just the new actual ride heights. I find the ride height, which takes the static wheel displacement and finds the change of the displacement. So how much did it change in your corner? And I just add those or subtract depending on it's left or right, and find those new numbers. And then I find the delta of how much it changed from static into your turn. So in this case, the inside lifted 11.98 millimeters, and the outside also lifted, but 3.24. And that's just telling me, taking the average of those, the delta moved up 7.61 millimeters. So the jacking force didn't keep the same ride height. It actually moved it up. And that's all from the jacking force. As you see, the outside tire had more jacking force than the inside. So the inside's trying to pull the chassis down, the outside trying to push the chassis up. And there's more force there, so the overall net effect is up. So one thing with roll centers is some people think the car rolls about the roll center, which is not true. It's a common misconception. They think you have a higher, I've heard, if you make your rear roll center higher than the front, then it has a diagonal weight transfer, taking like weight from the inside left and adding it to the front right, which isn't true. You can't have longitudinal weight transfer without longitudinal acceleration. So the front and rear total weights are going to always be the same if all you have is lateral weight transfer. So no braking, no accelerating, just going through a turn. Your total front and rear weights is going to be the same as if it was static. The only way to have longitudinal weight transfer is with longitudinal acceleration. So what I did here is I took different front view instant centers, the Z height, and then found at 0.5, 1, and 1.5 G's of lateral acceleration, how the actual point of rotation is moving about. And to find the roll point, I guess you could call it, roll pivot, it's not the roll center. I just took static ride height, then I took the dynamic ride heights here, and I found using a website. So I found this website, it's dummies.com, find the center of rotation. Basically it has these two different bodies and you're trying to find the center of rotation to get from that point to that point. And it walks you through it. So I just followed that and applied it to the suspension of my spreadsheet, and I'll kind of show you what points I used for that. So what we have is basically two sketches. One is the static ride height, which is at 50 millimeters, and then I drew a line of the chassis points of the dynamic ride height. So we have 70 millimeters on one side and then 10 on the other. And basically what the calculations to find the center of rotation do is you draw a line from one point to the other, and this line is at the midpoint and perpendicular to that line. So you draw one on one side, and then you do the same thing on the other side. Again, a point from the static ride height to the dynamic line at the midpoint perpendicular to that. And where those two lines cross, right here, that's the point that the chassis is actually rolling about. So I did that for different instant center locations and the different lateral G's. So basically, I'm just finding the roll point from static to 0.5 G, and then from 0.5 G to 1 G, and then the difference between the 1 G and 1.5 G. So it's just showing the roll location from one scenario to the next. It's not exactly accurate because it's not truly dynamic. It's using two static points to find it, but it's given us an idea of where the actual roll pivot is compared to the roll center. And I'll show you in the Excel of roll center compared to these different locations. So here I just plotted all these different Y and Z locations of that roll pivot. And it'll be at like 0.5, 1, and 1.5 degree or G's of lateral acceleration for different setups, and I'll talk through them. So first I'll look at the scenario where the front view instant center Z location is at 100 millimeters, which will be this line here. So this is showing the roll location of how it changes. So it's 50 millimeters up, and then it moves to the outside. So 0 center line, and it's moving roughly 100 millimeters to the inside. So remember, this is positive Y, so that's to the left. And then for all these, it's simulating a left-hand turn. And then compare that for the same suspension. It calculates the roll center to be right here at about 38 millimeters up and on the center line. So we're showing that's what roll center. It's not actually rolling about the center. It's rolling pretty far off from it. So it's showing that the roll center isn't the center of rotation of the vehicle. And there's just other scenarios I did. I put the instant center location down to 20 millimeters, and then I moved the inside one to 0, but kept the outside at 100. Then I swapped it around, moved the inside instant center location, kept it at 100 millimeters, but I moved the outside tires one down to 0 on the ground. So basically the outside would have no jacking force. And if we compare these two, they're closer than this one, where this is where the outside's basically having no jacking force, where you move the inside tires instant center, so it has no jacking force. It's a lot closer than when both are at 100. So it's showing that the outside tire has more of an effect on your roll and your jacking force, and here your roll location, roll point location. A lot of people kind of look at the roll centers and the migration of them, where they get like real hung up. They're like, oh, your roll center has too much migration, it's moving too much. Well, really, you just need to look at the jacking force. If the outside tire's jacking force remains consistent, then your car is going to have a consistent feel to it. Because the outside, since it has more normal load, more lateral force, it's going to have more of an effect on the jacking force of the car. I think an example of what I'm talking about might show better the effects of inside versus outside tire jacking force. So right now they're both left and right, the instant center locations 100 millimeters up. We can look at the roll angle 1.5 1.522. So we'll put that inside tire's instant center down to 0. So jacking force goes to 0. And the roll is still 1.552. So it changed a little bit, but not a whole lot. So move that back to 100. And we'll take now the outside tire instant center vertical location. We'll move it to 0. So the outside tire has no jacking force. But we see now the roll angle is 1.752. So it went up about 0.2 degrees. So there's a much bigger difference of moving the outside tire to 0 jacking force to the inside tire to 0. So if you want a consistent feel car, I'd say try to have that inline angle of the outside tire, try to remain consistent. All right, so now I'm going to show the difference of calculating jacking force through the A-arms, their actual locations, versus the end line. And all I did, I found the angle of the A-arms. If it would, there we go. So I took the two angles. And all I did was move the location of where the A-arms attached to the upright. So I made those kind of changes. I mean, I went to extremes to something like this. And I also changed the instant center location as well. Oops. To different points, and then did a few calculations of those different locations versus using the end line, and I'll show you the results of those. So what I did, I made different suspension designs, basically changing the point on the upright where it attaches, and also changed the instant center location once. But what we hear is just taking the A-arm angles where they attach to the upright and using 1G of lateral force, finding the reaction force through the A-arm, and then finding the vertical component of the force in the A-arm. So I did that for different upright locations, which changes the A-arm angles. And for a 100 millimeter instant center vertical Z height, I got all around 33 newtons, except for this one. It's a little bit lower, so it's 29.98. But since the end line only uses the instant center location for all of these setups, the end line calculations would all be the same, which is 33.94. So except for this one, it's all pretty close. Then I did one example where I took the instant center Z height and changed it to 500 millimeters. And I got 168 calculating jacking force through the A-arms, and with the end lines 169.7. So the end line is an approximation because it doesn't actually look at the A-arms themselves. It's just instant center location, but it's pretty close. So for simplification, I would continue using the end line just to simplify things. And just so you know, for all these, it's only looking at the outside tire. I just wanted to show the difference, so I just did the outside, didn't look at the inside, but they'd be all kind of similar as well. So before, we're looking at a single axle, and you can make a spreadsheet that is the front and rear axle, so your 4 tires, in pretty much the same way with a few differences. Same inputs, calculating jacking force the same way. You can make it as complicated as you want. For instance, this one, I added a load-sensitive tire, so as the normal load increases, the coefficient of friction decreases. And it's doing a loop with a dynamic corner weight, using an equation with the load-sensitive tire, and then making the lateral force of the tires And it's just doing a loop, because every time the basically solver, if you want to call it that, goes through a loop, it's going to change the dynamic corner weight, which changes the lateral force, which changes weight transfer and jacking force, which will then change dynamic corner weight. And you can turn iterations on in Excel, so it basically loops through until these numbers basically aren't changing each loop. The other thing to watch out for is the front and rear roll angle might not be the same. So what I had it do is use the solver in Excel, and I'll show you how to turn that on as well. Basically, the solver, you set an objective, the front and rear roll angle difference. I want it to be a value of 0, and it's changing this dynamic corner weight. You hit solve, it comes up with a solution where that is 0. And the dynamic corner weights, since it's changing this one, these are all equations based off of this cell, because this cell is going to be changing. So you need calculations for the right rear, front left, front or rear left to be based off this, but they still have to make sense. So we know the front and rear overall weight is going to be the same, and we know the left and right side weights after the weight transfer, what they're going to be. So these two need to add up to be the left weight, and again these two need to add up to be the right. The front and rear weights need to add up to be the same as the static front and rear weights, is assuming we don't have any longitudinal weight transfer. So you can see like this equation is just doesn't make sense, but once you look at it, it does. It's based off of this number here, or it needs to have the number in here, or else when it iterates this number, it's not going to work. And to turn on all of that, if you first go to formulas, you check enable iterative calculations. So you can set a number of times that it's going to loop through and the change that it's going to go through. So after 100 iterations, the solver just stops. There's not going to be any more. But for me, this worked for this spreadsheet. And for the solver, if you go to your add-ins, manage your Excel add-ins, you'll see the solver, and you'll click that, and it'll be under the data tab down here, or over here under solver. The other thing that I could have done with this 4-wheel spreadsheet is included the aeromap. Because we're getting front and rear ride heights, we can use those with the aeromap to then plug that in, and it'll just do more iterative calculations with the aeromap. Pretty much everything that I've been able to do with these static calculations, but now I'm going to move and show you how jacking force can affect the transients of your vehicle. To start off, I'll go over the model I'm using. It's a point mass, which is the blue circle. It's really just a dimensionless point that has a mass, so it'll just be the weight of the vehicle. Then in the yellow stick is the control arms, which I'm just modeling as one linkage, or thinking of it as the end line. And then in white, I have a spring, and in green, I have a damper. So all of those are going to be used in this transient model. For this instance, you see the suspension link, the yellow link, is straight horizontal, and then you have a force acting on it laterally, which is the red arrow. So think of that as the tire force going lateral. In this case, the end line is horizontal, transferring it straight to the chassis. And since it is horizontal, there will be no jacking. So the spring and damper do not move due to jacking forces. The next case is the suspension linkage has an angle. So there's still a horizontal tire force in red acting upon that linkage, but since it's now at an angle, there is a vertical component to that suspension linkage, which causes the jacking of the point mass. So the spring and damper will then have movement and speed. So how are we going to use this? Well, since there's a vertical component of the suspension linkage, that means the point mass is going to move up, because once static, part of the chassis weight is going to be suspended by the suspension linkage, and the other part's going to be suspended by the spring, as we saw in the spreadsheet. But what the spreadsheet can't show is as the point, or the chassis, in this case the blue point mass, as it accelerates up, there's going to be an increase in normal load on the tire. Since we all know force equals mass times acceleration, the mass is accelerating up, so there's going to be some kind of force, reaction force, down on the tire. So this means as it accelerates, we have more tire load. The force on the tire can be higher than the actual total mass of the chassis. So that's going to be an increase in normal load, which means increase in lateral force while the chassis is accelerating upwards. And again, once it stops accelerating, the total force on the tires is going to just sum up to the total force of the chassis. To help better explain this, I did a simple demonstration using a bathroom scale and me. Imagine my feet are the tires and my legs are the suspension links. So I'm starting in a down position, call that the static position. Think of your car fully setting on its springs. Then I push, accelerating upwards, and you see an increase of the weight on the scale. And that's during the acceleration of me moving up. You can see as I start to reach the top of my movement, acceleration then has to go towards the ground, which means equal and opposite. There's less weight on the scale. As you can see, the weight actually go down below the static setting, or static weight. And then once I settle at the upward position, the weight then settles back to what it started at the static weight. So the same thing happens with the car. As it accelerates up, you get an increase of normal load. As it reaches the top of the movement, acceleration actually has to reverse, where you get a drop in your normal load, and then you settle again at the load of whatever your static weight was to start with. So basically, my model is kind of demonstrating this, but in car form. So using a Python notebook, I solved my differential equations for the model that I showed you. So it has three different settings. So we have a horizontal linkage, one at 30 degrees and one at 60 degrees. And of course, damping, mass, spring rate. I just solved it and I got my different graphs. And I'll go through the ones that were kind of explain what's going on. First graph we're going to look at is the vertical acceleration of the point mass, or the chassis. So my model, the tire force is instantaneous, so there's no buildup. All of it's there already. You can see the vertical acceleration is positive for both the swing arm angles that have an angle in 30 or 60 degrees. And it starts high, and then vertical acceleration is still positive, but it starts to decrease. And you can see when it gets to the top of the movement, the top of travel, it then dips below zero, which is when we get the less normal load on the tire, and then it comes back up and settles at its static value. And to show you what vertical acceleration looks with less damping, I have this chart where if we look at both of the situations where the swing arm has an angle, starts positive, dips pretty down low negative, and then bounces back up because there's less damping, where again you get another increase in normal load or increase of vertical acceleration, which would increase the normal load, and then again settles out at a static number. Next we'll look at lateral acceleration. So how does that normal load affect the lateral acceleration from the increase of normal force on the tire? Situations where the suspension linkage has an angle, so it has jacking force, the lateral acceleration starts high, then drops low. You can see it dip down to where the vertical acceleration also dips. It correlates into the lateral acceleration, and then it settles out at a steady state value. Notice the scenarios where there is jacking force from a swing arm angle. The lateral acceleration is lower. That's from the CG being higher. We all know, or maybe you don't, it's okay. A higher CG will cause more weight transfer, which will in turn decrease your total possible lateral acceleration, and that's due to the tires not having a linear coefficient of friction, where coefficient of friction decreases with normal load. And there's other videos on YouTube that talk about tires and the coefficient of friction versus normal load, so I won't get into them here. But that's why here we see a decrease in that steady state lateral acceleration. Next, we're looking at lateral speed. So if you have an acceleration, you're going to have speed. Basically, in a turn, this will be how fast you're able to get through that turn, of basically traveling around the center point of the arc that you're traveling. You can see with the, we'll look at the swing arm of 60 degrees, the lateral speed is higher until a point where it's going to get overtaken by both the lower angle and then the one where the linkage is just straight horizontal. And of course, if you have speed, you're going to have some kind of position. Looking at this chart, the position of the higher swing arm angle is higher up to a point where it is then passed by the lower angle and the horizontal suspension linkage. So what does this mean? How do you translate this to a car and a track? Well, it's going to depend on the track you're driving. If there's enough time for, let's say, the horizontal suspension linkage, it is going to surpass the jacking force, the suspension linkage with an angle. But if you're in a tight course, like let's say autocross, you may benefit from having jacking force, because you'll gain acceleration faster, but know that you'll have a lower overall steady state value for lateral acceleration. And I'll show you some data to kind of have you think about that. Here's a screenshot of some data of lateral acceleration over time. It just has you think. The blue line has a lower end line angle, so less jacking force. You can see it has a higher overall lateral acceleration compared to the line in red, which has a higher end line angle, increased jacking force. You can see the red line, which is a car with higher end line, more jacking force. The lateral acceleration is wider on both sides of the turn, but with a lower peak. And I can tell you from this test, we're testing basically jacking force. We increased jacking force and our lap times went down, although our peak lateral acceleration was less. And this was an autocross course, so a lot of direction changes, not a lot of time spent at peak lateral acceleration. So you have to ask yourself, for whatever track you're at, would you rather be at 1.5 Gs for 1 second or lower 1.4 Gs for 1.2 seconds? It's going to depend on the track you're driving, of course, but you can think of that for your setups and what you're doing. And of course, there's more. You can either test this, or if you want to get into more simulation, you can create a simulation that incorporates this jacking force and transients of how fast does it get to your peak lateral acceleration. So it's not something I can answer here, but it's something for you to think and either test or simulate on your own. If you have any questions, leave them down below. I haven't seen any videos that go into jacking force on YouTube like I did, so that's kind of why I created this, and I'm hoping to start some discussion of maybe experiences or simulations you've done, or just questions on any of the methods and calculations I did here.